So we'll move on to our final of the longer talks before the student lightning talks. We'll hear from Vanessa Lowry.
All right, thank you. Hello, everyone. I'm Vanessa Lowry from the University of Central Florida. I'm giving my talk to you today on my recent work on T-matrix and HAPKE modeling of thermal infrared spectra of the Trojan asteroids. I have my co-authors listed right underneath the title, and I am currently being advised on this work by Carrie Donaldson-Hanna. All right, just a brief slide about the background and motivation as to why we should study the Trojans. The Trojan asteroids are two populations of asteroids that reside 60 degrees in front of Jupiter's orbit and also 60 degrees trailing behind Jupiter's orbit. This plot that I'm showing you are spectra obtained by the Trojans are highlighted in red, and those have been obtained by Dr. Joshua Emery using the Spitzer Space Telescope in 2004. And I'm showing this plot in order to emphasize the prominent 10 micron plateau, which is not a unique spectral feature. This is also shared between other solar system bodies. Cometary spectra have this feature, as well as other asteroids like 944 Hidalgo that I showed there in the bottom panel. In this work, I wanted to see whether we could model using widely spaced fine particulate olivine to explain the Trojan features. This is not an original idea. This was previously proposed by Emery et al. In 2006 as the cause of the 10 micron plateau, and also with cometary comay-like porosities. Although this is not the first attempt in trying to model the Trojan spectra, there have been attempts in the past, although I do not, to my knowledge, this is the first attempt to model using varying particle sizes and varying regolith porosities. So a quick slide about my methods before I get to the results. So in this study, I used T-matrix, multisphere T-matrix, and HAPKE reflectance models. Those are light scattering and reflectance models. I have shown two graphics under there giving you an example of what the input is required for T-matrix, being the optical constants, where I have phthalate, which is iron-rich, olivine optical constants shown there, and also my particle positions. So with T-matrix, you're able to specify your XYZ positions of your particles. So this is a good thing because I can adjust the porosity to whatever porosity that I would like to model. This makes up the bulk rectangular target. So I did this full process of modeling for 21 minerals, 21 separate minerals, and this number does not count 4 different porosities within each mineral, and also varying particle sizes too. So I made a huge big library of spectral library of individual minerals to see which one, and I plotted each one and did a chi-square minimization to see which porosity was selected. So I originally fit each one individually to see which individual mineral would show the best fit. I then used a smaller subset of the spectral library to use the weighted least squares, excuse me, to fit the Trojans. However, I had to go back and redo the modeling because the weighted least squares is not appropriate for fine particles or nonlinear spectra. It's appropriate for linear. So once I got the result from weighted least squares, I went in and redid the modeling to give what I call my final result. And onto the results. So this is 911 Agamemnon, and I used the NEDA model to fit the spectra to obtain the emissivity spectra. 911 Agamemnon is a D-type asteroid, and this asteroid lies in the L4 Lagrange point. So this is 60 degrees in front of Jupiter's orbit. I show the spectra in gray. So the measured in gray is the asteroid spectra with the model overplotted in blue. For this asteroid, the final result of the best fit, meaning the lowest RMS error. So what I did was, after going back and redoing the modeling, I would iterate and add more or less of phaolite force to right to find which one, using the T-matrix HAPKE, not using the weighted least squares, would give me the lowest RMS error. So for 911 Agamemnon, the 0.5 particle radii size fit the best with 100% abundance and an overall bulk porosity of 75%. The next asteroid I modeled was 624 Hector. This asteroid is in the same group L4 as 911 Agamemnon, the last asteroid on the last slide. Both were fit with the 100% phaolite at the 0.5 micron size. With this one was fit with a 70% porosity, so very similar to the last asteroid. So this could possibly suggest a compositional trend among the L4 group. However, a lot more observations and modeling is needed. And then the last asteroid is 1172 that I modeled using these methods. This asteroid is in a separate group from the last two. This one is in the L5 Lagrange point group, so 60 degrees trailing Jupiter's orbit. This favored the 1 micron particle size and the 0.5 for troilite. And you might be wondering why I have the 1 and the 0.5. So if an individual mineral fit the Trojan spectra especially well, I ran multiple particle radii to try to fine tune it. So this one favored the phaolite and forsterite. The bulk porosity here was, I have underneath in this table highlighted in yellow the porosities that I came up with using the weighted least squares originally. So then I averaged those three porosities to get the bulk porosity of 80%. So for this one, we believe that possibly that some intermediary olivine between the iron-rich and the magnesium-rich olivine would fit this spectra. However, to my knowledge, these obstacle constants are not available. And then the troilite was picked up by Aeneas. As you can see, the 12 micron sharp peak and emissivity is a little more smoothed out on this one. And also Aeneas has a more rounded 10 micron peak compared to the other two asteroids. So in conclusion, I broke this up into needed and not needed to be able to model the Trojan spectra. What was needed was mixture of iron-rich and magnesium-rich olivines, or one or the other. Also, we needed lunar-like porosity, so around 70 to 80% bulk porosity. What was not needed, that was previously proposed, was a fine particles of olivine embedded in a transparent matrix such as a salt. This was not needed. And then no ultra-high cometary Comé-like particle separations were not needed either. And that concludes my talk. And here's my email if you would like to contact me for any further questions. And thank you very much.
All right, great. Thank you so much, Vanessa, for a great talk. I really liked all your use of visuals there. It was great.
Thank you.
So we do have a minute. If anybody would like to ask Vanessa a question about her work that she just presented, you can feel free to type it into the chat. It's a little bit difficult for me to see raised hands in this format. But since we're kind of running out of time, I might just hand it off to Sean to introduce the next lightning talk speakers. And then if anybody has a question for Vanessa, please ask it in the discussion section at the end of this. And thanks again, Vanessa.
Thank you.
Yes.